Lab 3, Circuits, by Thomas Patterson. Introduction. The purpose of this lab is using the principles of energy conservation, loop rule, and current conservation, charge conservation, plus definition of steady state, you will predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuit, and examine the behavior of ohmic resistors and capacitors. Fundamental physical principles used in this lab: Ohm's law, definition of steady state, and Kirchhoff's loop and node rules. Assumptions made. Assumed battery resistor circuit was in steady state. Assumed resistance in connecting wires was negligible when creating potential graph across circuit, as that is what was shown in the lab instructions. Preview of results. The resistance of the 47 ohm resistor was found to be 53.33 ohms. The resistance of the 100 ohm resistor was found to be 113.33 ohms. The resistance of the wires was found to be 12.33 ohms, and the resistance of the ammeter was found to be 1 ohm. The bulb in the RC circuit with the battery was bright when the capacitor first was connected and then slowly dimmed and went out as the capacitor charged. The bulb in the RC circuit without the battery was bright when the capacitor first was connected and then slowly dimmed and went out as the capacitor discharged. Experiment and calculations. Here is a photo of our experiment. As you can see, the multimeters are set to reading current right now and are put into the circuit in series to see what the current flowing through the circuit is. The multimeters were also used for other things, such as checking the potential difference of different parts of the circuit. Here is a photo of the RC circuit. As you can see, in one photo, it is hooked up to the battery and the capacitor is charging, and in the other one, it is not hooked up to the battery and the capacitor is discharging. In this experiment, these circuits were the system. Data. The currents at I1 and I2 were both negative 15 milliamps. When the ammeter connections were reversed, the current became 15 milliamps. This means that the current is 15 milliamps and that the connections were originally just connected in reverse. Potential difference across both batteries was 2.7 volts. Potential difference across the 47 ohm resistor was negative 0.8 volts. The potential difference across the 100 ohm resistor was negative 1.7 volts. The magnitude of potential difference across the X-Tech X410 multimeter, the multimeter used in this lab, has a 1-to-1 ratio with the magnitude of current flowing through it. Charging of the capacitor took around 15 seconds, and the discharging of the capacitor took around 9 seconds. Here are our calculations. We applied Kirchhoff's node rule. The sum of current in is the sum of current out, and then we applied Ohm's law to find the resistance of different parts of this circuit. We applied Ohm's law to the 47 ohm resistor to find it to have a resistance of 53.33 ohms. Since the circuit is in series, we know that the current is the same everywhere in the circuit, that being 0.015 amps. And then we used this to find also the resistance of the 100 ohm resistor. And then we used the fact that we know that there is a 1-to-1 ratio of the potential difference of the multimeter and the current flowing through the multimeter to be able to apply it to Ohm's law to calculate that the multimeter has a resistance of 1 ohm. And then we used Kirchhoff's loop rule to sum up what the potential difference of the wires must be, because we know what the potential difference of every other component of the circuit is. And then we applied that to Ohm's law to figure out what the resistance of the wire must be. Discussion and conclusions. Here is the electric potential throughout the circuit. As you can see, it never reaches zero because in this graph, in the lab instructions, it assumed that the potential difference of the wires was zero, and so that is what I also did. And in doing that, the Kirchhoff's loop equation will not be fully satisfied, and the total voltage will never go to zero. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? This is because of node rule, as the voltmeter was connected in series. Results of the battery resistor circuit lab. As you can see, here's what the resistance of each component was found to be. And these results are interesting for multiple reasons. One, because the 47 ohm resistor is not 47 ohms and the 100 ohm resistor is not 100 ohms. However, both of these calculated values are within 15% of their expected values, so this is nothing of large concern. What else is interesting is the fact that the resistance of the wires was found to be 12.33 ohms. This is almost 1/4 of the resistance of the calculated value for the 47 ohm resistor. With this, the argument could definitely be made that for this circuit, the wire's resistance should not be considered negligible, which they often are for circuit calculations. Additionally, the resistance of the ammeter likely could be considered negligible, as it has a resistance of less than 10% of even that of the wire. Results of RC circuit lab. The bulb in the RC circuit with the battery was bright when the capacitor first was connected and then slowly dimmed and went out as the capacitor charged. This took about 15 seconds. The bulb in the RC circuit without the battery was bright when the capacitor was connected and then slowly dimmed and went out as the capacitor discharged. This took about 9 seconds. This makes sense as the capacitor is hooked up to the circuit with the battery. When it initially has no charge, it does not impede current flow whatsoever, but the more it charges, the more it impedes current flow until the point where current flow becomes zero and the light does not shine. And then when you make a circuit not containing the battery and just the capacitor will discharge, and then as it discharges, its charge becomes less and less until its charge of zero, and then there's also no current. Possible sources of error. Any of the assumptions made for this experiment were not true and led to a significant difference in the result. Rewind the video to the assumptions made section for more details. Error in calculations, human error when conducting the experiment, assumed incorrect resistance and or potential difference across multimeters. What if? To answer this question, we need to apply the formula tau equals RC, which basically says that the time, tau, it takes in seconds for a capacitor to charge or discharge through a resistor is the product of the resistor's resistance in ohms, R, and the capacitance of the capacitor in farads, C. If a capacitor was charged in a circuit with no resistor, R equals 0, the capacitor would reach full charge instantly, tau equals 0. This would not occur in real life as there is no such thing as a circuit with no resistance. Connecting wires and batteries both have resistance in the real world. Thank you so much. Have an awesome day.